high dimension case. Okay, so substitution. Okay, so if you have, suppose you consider an integral one dimensional from a to b f of x dx, right? And this function is complicated. You want to use substitution to simplify. So this is the interval from a to b. The so-called substitution is this is alpha and the beta. Okay, this is t variable. You have a map, but this map could be this is x. X is going to be h of t. But it's possible alpha is mapped to A and the beta is mapped to B. But it also can be possible to change the orientation. Okay, but as long as the image of the interval from alpha to beta is the interval from A to B. But it's possible the derivative is negative. Okay, when the derivative is negative, then you have to switch the derivative negative means the beta goes to A, alpha goes to B. Okay, in that case. So I did not say h of alpha equals A. H of alpha could be B. Okay, so the integral of this integral can be become h of t here, and then h prime t dt. But we have to be careful. If I still use alpha to the beta, then I put the absolute value here, because if it's negative, I change the order of the orientation. Okay, order of those two numbers, alpha and the beta. Okay. Then we always have this formula true. Okay. This is obscure. Everybody knows that, right? When h prime t is negative, when it's decreasing function, that means alpha is going to be B and the beta is going to be A. Okay. All right. So for high dimension, right? How do we do that? For high dimensional, you have let's look at the triple integral, not again double integral. Okay. The triple integral, I'm going to use let's use E, right? Yeah. So notation. What's the notation for the domain? With the traditional notation. Yeah, E. Okay. So here's the E, and this is a function f, x, y, z, and z. Let's consider that. So either E is very bad or f is very complicated. Okay. So we're going to modify it to another interval. So in here it's three-dimensional. This is the E, very complicated, right? E. Okay. And if I can, this is x-axis, y-axis, z-axis. So I'm going to use, let's say, UVW. Okay. So maybe I get a very nice one here. Usually it's a nice one. Okay. A domain and the E bar. Right. So I have a map. So you think about, I'm trying to compare, but this time the map will depend on three variables: UVW, y is going to be y, UVW, z is going to be ZUVW. Okay, so it sends E bar to E. So what kind of formula I'm going to set up? So this triple integral, okay, we have a very similar formula. Okay, f x y z dv is going to be the integral right now over E bar. Okay. What else? So f here, x is still x, y, z, but this will determined by those formulas. Okay, so it's a function of UVW. And then how can I put I cannot just put a dv bar here. Dv is going to be dx, dy, dz. Okay, in some sense. Okay, so then I have to put another one similar to this one. Okay. So now I have a three parameters. So this will be the absolute value of the partial derivative of these three variables with respect to the three variables. Okay. Then dv bar. So dv bar is going to be du, dv, dw. So now you understand the formula. Okay. If we compare to the other one, now what is Yeah, what is the partial derivative of x, y, z with respect to UVW? This is matrix, right? So this is a matrix. It's not just a, this is a determinant of the matrix, okay? It's going to be the determinant of this matrix. So it's going to be, let's say U, okay? Then you differentiate with respect to, it doesn't matter which one is first, yeah, with respect to V, and then the X with respect to W, Y with respect to W, and Z with respect to W. So you have to compute this matrix. Compute this matrix, then find the determinant. So you get a function of UVW. So this is a very general formula, okay? And the reason we want to do that is in many cases, like you can change the shape of the domain, okay? The region, yeah, E. Sometimes the region, no, the best region is a rectangle, right? We want a rectangle region. But sometimes the region is a cylinder, sometimes it's a sphere, or sometimes a triangle, something. So this is a general formula, okay? And if it's two-dimensional case, then dV will be dA, and you only have two variables, x, y, and then uv. Okay. All right. So today's topic is section 15.7, cylindrical coordinates. So-called cylindrical coordinates is just a map. Okay. Suppose the domain E is a cylinder. Okay. So the domain E is a cylinder, such like that. Okay, so I'm going to draw, yes. Okay, so let me, cylinder, right? So this is in the X, Y, Z plane, and here's this is E. But the cylinder can be, we know the circle is coming from the rectangle. So we can get, this is Z, that's R and the theta, okay? And the theta. So the idea is this will be, you get a rectangle, okay? Yeah. It depends on how deep it is. So Z is the same Z, okay? But as the square becomes a circle, as a rectangle becomes a circle. So the map is as follows. X is R cosine theta. If this is a radius, is capital R, okay? And the Y cos R sine theta. Z is still equal to Z, okay? That's it. So here, see, theta is between 0 and 2 pi, right? R is between 0 and R, and the Z still is between, let's say, use the A and the B, as it doesn't matter, right? So you can use A and the B. So theta, R, Z, those are the parameters from a rectangular box. We like this rectangular box, right? And that's E, right? And then triple integral of a cylinder becomes a triple integral of the rectangular box. Then that's much easier to handle, right? Use the iterated integrals. So this is going to be, let's write down the formula, okay? So here, f x y z dv will be the triple integral over this rectangular box, and here x can be replaced by cosine theta, I replaced by sine theta, and z is still z, and the dv bar. Okay, dv bar is d. Now don't forget we have another determinant, but after we compute, the determinant is just r. Okay. So here, let me say dv is just essentially dy dz, dx dy dz, and here dv bar is going to be dr d theta dz. Okay. So this is coming from the determinant of the matrix. It's easy to compute. Right? It's easy to compute. You can check that. Let's do this computation. Okay, x, y, z, r, theta, z. Okay, when you compute the matrix, that's the determinant. The derivative of x with respect to, I think r is first, right? With respect to r, that would be cosine theta and sine theta and z. The second one is the derivative with respect to theta. So it's negative r sine theta and r cosine theta and 0. The third one is derivative with respect to z, 0, 0, 1. Okay. So when you find, how do you compute a 3 by 3 matrix determinant? Right, this both are all zeros. So actually, this is given the determinant of just the cosine theta, sine theta, negative r, sine theta, cosine theta, and which is going to be just r. Okay, that's just the determinant matrix. Okay, if you forgot how to find the determinant matrix, 3 by 3 or 2 by 2, then you just look at the book you used for Math 171. Okay. Okay. So when you put a determinant, they just put that. So this is a formula given in the book. I just trying to tell you where this formula from. Just list it there. Okay. Understand that this is a kind of substitution anyway, right? It's a substitution, but more complicated because it also have to take care of the domain. There's a region. Yes, a region in 3-dimensional space. You have to, not only just simplify a function, you have to simplify the region. In the 1-dimension case, the region is just interval. It's simple, just the two end points are quite different, right? But the interval, it's intervals. The geometric picture is simple. But in 2-dimension, 3-dimension cases, the region is very complicated, right? So substitution becomes more complicated. So we only consider some special cases. Okay. All right, so that's it. So now we're going to do the problem. Okay. Now once you get this triple integral over the E bar, which is a rectangular box, then you can use the iterated integrals, okay, to evaluate this triple integral. Okay. Sometimes, of course, if the function itself, it's possible, E bar is not a rectangular box, right? Because E itself is not a perfect cylinder. Maybe cylinder cut through by the plane, something like that, right? So you just be careful when you describe this E bar. Okay, this depends, but you can also extend the function f to all sides of E so that E itself will become a perfect cylinder, and then the function is 0 outside this E. So you can change that. Okay, but right now let's just consider this special case, and then we will see how do we solve the problems. Find a good Let's look at examples first. Okay, describe the in words the surface whose equation. Well, this is 7 point. Right. So write equations in cylindrical coordinates for the following equations. The first one is 2x squared plus 2y squared minus z squared equals 4. Okay. The so-called cylindrical coordinates just as a transformation. Here, x equals r cosine theta, y equals r sine theta, and z equals z. Okay. Now this surface, yeah, what we're trying to do is, this is a surface in the xy coordinate system, right? Right. Some surface, right? Some surface. It looks like maybe looks like that, right? I can draw a couple of them like that. Okay. So a surface in the three-dimensional XYZ coordinate system. So we know there's a map between, right? There's a map here, right? And so we want to see the pre-image of this surface in this R theta Z coordinate system. Yeah, in this R theta coordinate system. Oh, it's funny, in the book it does not draw the coordinate system even. Okay, that's fine. I prefer the more geometry pictures here. Right. So yeah, you know, the reason I want to look at it, sometimes they write the theta on this side and r theta r z, but in this case I prefer r theta z. Okay, so you just plug them into the above equation. You get 2r square cosine theta square plus 2r square sine square theta minus z square equals 4, right? So after simplifying, you get 2r square minus z square equals 4, okay? What does that tell you? That tells you how does it look like? Z square is going to be 2r square minus 4, right? Okay. This is actually is a hyperbola in the RZ plane. This is a hyperbola in the RZ plane. If you divide both sides by 4, it'll be r squared over 2 minus z squared over 4 equals 1. Okay. This is a hyperbola. Let's draw the hyperbola. So when z equals 0, I is going to be plus minus square root 2. Okay. So I think this will be pictures like that in the RZ, in the RZ plane. No restriction on the theta, which means you are going to get, yeah, it's very difficult to draw it. You're going to get two pieces. Can you visualize? Yeah, two sheets like that. Okay, it's hyperbolic sheets. Okay, and there's two pieces. Okay, those two pieces, and the above map was sent to two surfaces like that above. Okay, and yeah, x. Yeah, it's hard to understand. Hold on, I made mistakes. R and no, yeah, it's okay. Yeah, z equals r squared. Yeah, no restriction on theta. I think so. Yeah, but these two sheets, it's hard to imagine. Theta is between 0 and 2 pi, so you stop here. There's only one piece. It's not like, you know, goes to infinity. So these two pieces, how can you make these two pieces? I'm trying to understand. Yeah, it's hard to see. Yeah, how to make these two surfaces? You know, you just have to compress one end, okay, and you have to close up. Yeah, it's harder to see. Okay, so the idea is which curve goes to where. You know, this is a this. Let me draw the curve. Okay. So when this line, I think it goes to when z equals 0, I is going to be fixed. So let's see. Yeah, so you will get a circle. I just hope that bend it like that. Yeah, anyway, it's hard to see that. So this is a picture. Write down the equation. We just need to write down the equation. You don't need to visualize as a graph. Okay, so this is the equation in the R theta z plane. Okay. Yeah. Yeah, in the R theta z plane. It's cylinder actually, but there's a cross section where we have a hyperbolic curve. Okay. All right, so next one, sketch the solid described by given inequalities. Okay. Problem number 12. Right. Now, without using sketch solid, actually sketch solid in 3-dimensional space. Okay, in the XYZ plane. Right. But the picture in the R theta z system, this is going to be theta is between 0 and pi, but the I is there any restriction R? No. Yeah, z is just like assuming theta is 0, z is between I and the 2. So z is between I and the 2. I think this will be the triangle like that. Z is between I and the 2. Okay. So in the cylindrical coordinate system, okay, this will be a picture. Okay, this is a region, and it's going to be pi over 2. Right, so it looks like that, and I'm trying to draw. I'm not good about drawing 3D picture, but this is what I can see. Okay, it's like a piece like that. Okay, yeah, and this line is going to be z equals r. Okay, so the lower, the smallest value for z is going to be r. The largest possible value for z is 2. Okay, if you draw the vertical lines here. Okay, so how can I describe the picture over there? Well, you have to do the in the cylinder, but z is between 0 and 2. Okay, so theta is between 0 and pi, so just only half of the cylinder. Right, a quarter of the cylinder. Yeah, theta. So The problem is you have to make sure I is going to be, it depends, this depends on the R value. When I increases, Z increases. So yeah, when I equals 2, Z is always equal to. You don't have just only the small pieces. So my understanding is you have to cut that piece. It's hard to draw the 3D pictures. Let's see. Z is between R. So let's draw this. Say this is a circle R, right? With radius R. Then Z inside Z is between R and 2. So yeah, these pieces are inside in the solid. Think about that. So the real picture will be looks like okay. That's my understanding. In the X, Y, Z system. Okay, and for any circle here with radius R, and these values between R and 2, right? That's clear. Okay, so this is a picture. Now, without using the picture, how do you describe it? X equals R cosine theta, Y equals R sine theta, Z equals Z. Okay, so R is going to be X squared plus Y squared, right? So in other words, the Z value, is between I and 2. So between I and 2, so first of all, Z is greater than or equal to R. It's going to be square root X squared plus Y squared. Okay, and Z is also less than or equal to. Then all you have to do is to understand, trying to understand the picture. Yeah, what is the graph, right? How does the graph look like? Z equals square root X squared plus Y squared. It is cone, right? It is cone. Okay, the graph of this is a cone, right? The graph of this is a cone. It's cone-like. Yes, it is cone, right? So it is cone, and then I know that theta is between 0 and pi over 2, so I divide the cone into 4 parts. Then this is in the first octant. Okay, just 1, 2. So you can understand the graph as solid in a different way. Just use rewrite the inequality using X, Y, Z coordinates. Okay, then you see that for any fixed Z, X, Y, Z is between square root X squared plus Y squared and 2. Okay, but the Z equals square root X squared plus Y squared is a surface, right, which is cone. Okay, so we get the same picture, but we're doing, but it's hard to see how do we make from here to here. You see, that's a map, the cylindrical map maps this triangular cylinder to this cone. Okay, think about how to do that, right? I think when theta equals 0, all the side is collapsed to this side. Yeah, this piece collapsed to 1 point. Okay. Then which p then you make when theta changes. No, I close it. No, that's not. Yeah. So this triangle, yeah, you're trying to understand where this triangle go. This triangle will be these between. I think that pieces will be theta is going to be 0, so it will be this piece. Okay. Yeah, this was from 0 to 2, and the theta is 0, so okay, and yeah, that is a piece. Okay, and the other side. Yeah, this side of the triangle goes to the other side because the first of all you make sure where the theta equals 0 is this triangle, and over there theta equals 0 does not locate it, so in the xz plane. Yes, in the xz plane. So this is we just determine the correspondence between those two surfaces. All right, so using two different ways, we can figure out the solid in the space. Why we have to do that? Because sometimes as the solid is described by the coordinates in the cylindrical coordinate system, or sometimes in the XYZ coordinate system. So we're going to in order to evaluate the triple integral, you have to understand the picture. Okay. All right. So now I'm going to do number 18. Evaluate this triple integral. Okay. And the E is included by the paraboloid z equals x squared plus y squared, and there's a plane z equals 4. Okay. So let's draw the picture here. First of all, what is that? Is in the xy coordinate system. Right? Well, yeah, we're trying to set up a integral to. So z equals x squared plus y squared is this paraboloid. Okay, and it's 4. So that means it's cut by this horizontal plane z equals 4. Okay. That's the E. Now, without using cylindrical coordinate system, okay, how do we evaluate this triple integral? Okay, the way we do is there are two different ways. Well, let's set up the integral. Okay, we can we can use the integral like that. So this dA, and I think is dz. Okay, so look at this. The projection to the xy plane. This d is going to be x and y, x squared plus y squared less than equal to 4, right? Clear? Yes. So for every point x and y in the D, I have to draw a vertical line, and then I'm going to going through the solid. So I want to determine the upper bound for the z, lower bound for the z. And clearly, the upper bound for the z is going to be 4, right? The lower bound for the z depends on x and y. So this will be the iterated integral for this triple integral. All right. Now, how do you evaluate that? Right. Double check. Okay. So the solid in three-dimensional space can be filled up by this vertical sticks, right? Bars, right? So those vertical sticks, right? Is above the domain D. The domain here is x squared plus y squared is less than or equal to 4 because the largest possible value for z, this disk on the plane z equals 4, is given by the equation x squared plus y squared equals 4. So that's why clearly the D is going to be given by that. All right. So then for every point in the domain D, right, for every point in the domain D, and you draw this vertical line segments going through the solid, and you look at the values for the Z, upper bound, lower bound. So the lower bound is x squared plus y squared because it's coming from this paraboloid, and the upper bound is 4. Okay, then you evaluate it's a half of z square and evaluate at 2 end point, then dA. Okay, then you will get when z equals 4, 16, so divide by 2, 8, then half of x squared plus y squared and dA. Now, in many cases, you don't need to have cylindrical coordinates. You get a double integral. For this double integral, you can use the polar coordinates. In my opinion, polar coordinates are just the cylindrical coordinates, just add one dimension, trivial dimension, just z equals z. Okay, so for the polar coordinates, now you can using x equals r cosine theta. See, y equals r sine. This is actually part of the cylindrical coordinates. So cylindrical coordinates it's not essentially different from the polar coordinates. So this is going to be the integral of a d bar and 8 minus half of r squared and r here, and the dA bar. dA bar is going to be dr d theta. So you can use 0 to 2 pi, 0 to what is r? R is 2, okay? 8 minus half of r squared, r and dr d theta. All right, so it's nothing to do with the theta, that's why you get 2 pi. And the antiderivative of this is 8r minus half of r cubed, so it'll be 4r squared minus 8r to the 4th power. So when you differentiate, you get, yes, you get, yeah, I don't use the integral symbol here because I already found the antiderivative if I want, okay? So I did it quickly, yeah, get rid of all the 2 integral symbols. Yeah, theta, whatever's inside is independent of theta, that's why you get 2 pi. And then you have to find the antiderivative of 8r minus half of r cubed. Okay, then you evaluate this integral. It's going to be 4 times 2 squared minus 8 times 4, 2 to the 4th power. Okay, and let's simplify. 16 minus 2. Yes. So 14 times 2, 28 pi. Right, so you get that. But of course, you can say, I want to use a cylindrical coordinate, but you will end up with the same double integral, triple integral, because when you look at this, yeah, let's go back to this picture. Okay, let's look at this picture. Now you are going to use so-called cylindrical coordinates, right? Okay, but you have to describe this solid, right? So the cylindrical coordinates, the surface is going to be z equals x squared plus y squared is equivalent to saying that z equals r squared. Okay, it's equivalent to saying that z equals r squared because x squared plus y squared equals r squared. Okay, so if you want as a solid, this is E, right? The E is determined by x, y, z, right? And I think z is between what do we get here? So z is between r squared and 4, I think, right? Because it's between x squared. Sorry, first of all, you have x squared plus y squared, right? So this is a given information, okay? But this can be described by this is a map, right? You have the cylindrical coordinate system, okay? But in the cylindrical coordinate system, you have a cylinder actually. You will get a cylinder mapping to it. No, it's not. I shouldn't say cylinder. It's not a cylinder. So it's theta is going to be between 0 and 2 pi. I is between 2 and yeah, actually is going to be a rectangular box. So that's the E bar. Let's describe E bar. R theta Z, okay, and Z is between R squared and 4. That's it. And there's no restriction. There's no restriction between for theta. So theta is between 2 and pi. Okay. So what does that mean? That means we actually have a we actually only consider this piece. Right? We only consider this piece. So this solid E is mapped to the above solid. Yeah, Z is between R squared and the 4. Okay, so the triple integral E and Z dV is going to be the triple integral E bar, and the Z is going to be still Z, but dV bar, right? And then multiplied by R. Okay, but for this triple integral, you still have to change it to the double integral. Okay, it's not a rectangular box; it's just a portion of that. But the good part is, it depends on how do you do that, right? If you still want to use that one as a D, yeah, if this is a domain called a D bar, right? Then this will be D1, and Z is still Z. Yeah, so DZ is ZR. Z start from, I think Z start from R squared to the 4, and the D A bar. Okay, D A bar is DR DC. So now let's evaluate this. Here's r, and it's half of z squared. It's that from 4r squared, and we will get the same. We'll get the same result because this would be 4 squared minus r to the 4th power, right? Right, and then we have r. Wait a minute, we have r to the 4th power. Did I make a mistake somewhere before? Okay, I'm going to double check. I'm trying to see. Yeah, let's go back to here. That's possibly, that was a, I saw the mistakes. All right. When I put, because z is between x squared plus y squared, and between to the right, I should put a square here. Okay. No, then the answer would be different. So this will be r to the 4th. Yeah, this will be r to the 4th power. Okay. Yeah, this will be the r to the 4th power instead of square. That was, yeah. So the number will be different. Let me change it. Right, let me recalculate this. Oh, you caught that? You were watching me, so it's easy. All right. So now you multiply this out. That will be fifths. Okay. So the entire derivative will be 4r squared and minus that will be 12r to the power 6. Okay. Yeah. Now it's correct. 4 times square, 12, and the 2 to the 6th power. Okay. Yeah, we should end up with the same integral. I'm not going to finish that part. Yeah, this is 16 minus, that's a fraction. So you will end up with the same integral. Okay. And here d bar is this r, and the theta is just this is going to be 2, and here's 2 pi. Okay. So that's a d bar. So yeah, then a dr and d theta. Okay. So you end up with the same integral again in any case. So cylindrical coordinates are essentially is a polar coordinates, but just you give one more freedom variable z here. Okay. So you end up with here's 2 pi, then the entire derivative was yeah, this is r, and so it's going to be divided by 2r squared and 1/6 r. Okay. Evaluate 2 in the points, and you get same result. Okay. Yeah. So you will get 2 pi. If you multiply this out, that is going to be 4 times 2 squared minus 12 here r to the power 6. All right, so you get same result. Let's take a look at the number 22. Okay. Find the volume of the solid that lies within both the cylinder x squared plus y squared equals 1 and the sphere x squared plus y squared plus z squared equals 4. Now this time I'm going to use a cylindrical coordinate system. Okay, but I have to draw the picture for the solid in the xy plane. Okay, x squared plus y squared equals 1 is a cylinder. Okay, and the sphere has a radius 2. So you will get this portion of what does it say? Lines within. That's weird. I think I should say between this cylinder and the sphere. Okay, within the cylinder means it must be inside the cylinder. Okay, so I think within this between those two surfaces somehow. Yeah. So this is a region we're talking about. Okay. Now, of course, you can if you find the volume of the cylinder inside the sphere, then you use a subtraction, you get the remaining part. Okay. Let's describe. All right, let's continue. Let's disconnect it for a few minutes. Okay, so I equals cosine theta, y equals r sine theta, z equals z. Okay, how do we describe? How do we describe it? The lines within the both cylinder, x squared plus y squared. I think, yeah. So x squared plus y squared equals 1 is the same as r squared equals 1. The same equals r equals 1. Okay, that's easy. Okay. So x squared plus y squared plus z squared equals 4 is the same as x squared plus z squared equals 4. So how can I describe the region, right? It's all sides of the cylinder, so it must be greater than, right? I change the greater than equal to all sides of the cylinder. So it's greater than equal to 1. So that means you just change the encoding. The inside the sphere, it's less than 4. It's less than 4. Okay? And what is the no restriction of the theta? So theta is definitely still between 0 and 2 pi. Right? Think about it, right? So r is greater than or equal to 1, but r squared plus z squared is less than or equal to 4. So let's look at the picture just in the r and the z place. Okay? R squared plus z squared equals 4. So that is a circle with radius 2, right? And r is greater than or equal to 1. Okay? So that means r is greater than or equal to 1. That piece. Okay? So that is a piece, right? So here, yeah, r squared plus z squared equal less than or equal to 4. R is greater than or equal to 1. Right? So that these two equations describe that region. All right. So now That's good enough, right? And how do you describe the new domain for the in the cylindrical coordinate system? So the new domain is the cylindrical coordinate system. Okay, here's R, here's a theta, right? This is a Z, right? So first of all, let's look at the sphere. So this is a portion I'm talking about, right? So theta here is 2 pi. Yeah, that is a piece of the domain E. All right, so let's look at the volume. The volume is going to be the triple integral of E, right? This triple integral is going to be this triple integral of E bar. And here will be R and then dV bar, okay? Right? By the cylindrical coordinate system. The cylindrical coordinates, using cylindrical coordinates, you get this. And so the E bar can be described by these two equations: R squared plus Z squared less than or equal to 4, I is greater than 1, theta is between 0 and 2 pi, okay? So these are called the D, right? This is a D, right? And you can yeah, how do you you can write down the 3 iterated integral directly, no problem, right? So for example, theta is from 0 to 2 pi, and d theta, right? And but you have to say I is between 1 and 2, so dr, and then you have to figure out what is dz. Z, as you know that from that above encoded, Z squared is less than or equal to 4 and greater than, right? Z squared, there's no restriction on the Z. No, you cannot use it that way. You have to change it to how to describe this, right? Z, actually, you have to say R squared less than or equal to 4 minus Z and greater than or equal to what? 4 minus Z squared, yeah. Okay, then because R squared is, yeah, then you have to change it to so dz first, okay? The smallest possible value for Z is going to be the smallest possible value for Z. You can look at this picture, it's better. Yeah. How do you evaluate the double integral on this D bar, right? Double integral on this D bar, right? You can say I is between. Oh, there are a couple ways to do that. Yeah, you can use you can let the Z between this number, which is going to be when I equals 1, that's a negative square root 3 to positive square root 3, and for each Z you figured out the R value, right? So you can, yeah, you can start from negative square root 3 to positive square root 3. Then R is between 1 and the number determined by Z, okay? So which is going to be square root of 4 minus Z squared. And here's dr. Okay, this is one possible way. Another way to do is you still use R start from 1 to 2. Okay, and you have to figure out the Z. When you look at this picture, again, right? When you look at this picture again, here is right. This is yeah. How do you describe that? R is between 1 and 2. For each R, the circle is R squared plus Z squared equals 4, right? So you can tell that when for the fixed R, Z is going to be negative square 4 minus R squared and positive 4 minus R squared and then dz. Okay, so we have here R here. Don't forget the R here. So in either case, you got the triple integral, yeah, iterated integrals. Okay, what I'm doing here is I write down the triple integral, iterated integral directly. If you do step by step, then you have a double integral over, yeah, you will get something like that. Double integral and R dA bar and d theta. Okay, so this is a d bar. Yeah. Now, which one is better when you evaluate? I think the second one you have to use a substitution. How about the first one? The first one here, yeah, you don't need to use substitution. So you will get antiderivative half of R squared, then you take a difference. Okay. So the volume, let's finish the computation. Okay, let's use this. Okay, let's use this one. Right, it's going to be antiderivative of this will be R squared, right? Okay. And that will be R squared, 4 minus Z squared, minus 1 squared, it's just 1. Right? And that will be 4, that's 1/2, right? So that will be half of 3 minus Z squared. So the antiderivative will be 3Z minus 1/3 Z cubed. Okay. That's my experience. So just double it. Okay. Forget this is a Z square of 3 minus 1/3 square of 3 and cube. Yeah, twice of that, so 2 is cancelled out. Right, so that will be just 2 pi times the number 3 square of 3 minus 3 over 3 square of 3. So it'll be just 2 square of 3, right? And 4 pi square of 3. 4 pi square of 3. So that is oops, this is the value, the volume. Okay. Okay, let's go back to this problem again. Yeah. Okay, we try to find the volume of the solid, okay, and it's described by those two inequalities. Within the cylinder and the sphere means it's determined by, this solid is determined by two equations, x squared, two inequalities, greater than or equal to 1, and x squared plus y squared plus z squared is less than 4. Okay, it's completely determined by these two inequalities. And if you don't know how to draw the graph, you just write down the three equations, okay? And trying to figure out the two inequalities in the cylindrical coordinate system, which is r is greater than 1, and r squared plus z squared is less than or equal to 4. So that means in the, no restriction on theta. Theta is between 0 and 2 pi. So you just needed to draw the picture in the r theta z system. Okay, the domain. So the domain is actually this piece of it's kind of cylinder, but we cut off one side. Okay, this is just like a round, a piece of round wood, right? And you chop, take one slice, okay, and you try to evaluate the triple integral of r over that region, okay? Then you use iterated integral to evaluate. It'll be much easier, okay? Right? It'll be much easier. Otherwise, it's very difficult to change the iterated integral. It's the original one. How can you do that? This original one, the E is described by these two inequalities. It's not easy to, anyway, it's not easy to write it as iterated integral. Now for this one, it's easy to write down the iterated integral. You can try a different way to write it, okay? So let me draw the picture again. I have a couple minutes. This is a r, theta, and the z, right? If I'm supposed to have, so this is a piece I'm going to cut, right? Yeah, this is a piece I'm going to eat. Suppose you have this triple integral, right? R and the d v bar, right? How do you evaluate? Okay, so I'm going to denote this part as a d bar, okay? So d bar is going to be r and z, and z is I is greater than or equal to 1, z is less than or equal, r squared plus z squared is less than or equal to 4, okay? Right? Now, how can I describe it? This is a 2 pi here. So the integral is very simple, just equal to d bar. And here's r. I'm going to evaluate theta and the dA bar, okay? And theta is from 0 to 2 pi. For each point in d bar, theta is between 0 and 2 pi because those lines, horizontal lines, the domain for the theta is from. So you get 2 pi immediately. So then you get this double integral. Okay. Then you just focus on this double integral, and then you look at the picture again. Here's r, here's z, and this is a picture, and this is your domain d. Okay, from 1 to 2. Then you have two different ways to write the iterated integral for the z. Okay, and you can start to fix as r from 1 to 2, dr, then z should be between the lower bound and the upper bound, right? Z is going to be 4 minus r squared, square root 4 minus r squared, negative, and 4 minus r squared positive, and I and the dz. Okay, so this is a rough idea to iterate this double integral. This triple integrals. All right, so in the next class, we are going to study spherical coordinates. Same idea, just substitution. It's the three-dimensional substitution. All right, see you next time.